Introduction to Satellite. Satellite is a celestial body that revolves constantly around another celestial body. In our solar system, different planets revolve around the Sun. So, planets can be said to be the natural satellites of the Sun. The Moon is the natural satellite of the Earth. So far, many artificial satellites, that is, man-made satellites, have been launched. The satellites are put into their respective orbits with the help of multi-stage rockets. Artificial satellites are used for communication purposes, for weather forecasting, to study various phenomena in the outer regions of the Earth's atmosphere, for topographical purposes. A satellite which remains stationary with respect to a fixed point on the surface of the Earth is called a geostationary satellite. These satellites are used for communication purposes. The application of satellite in everyday life has become so immense that the study of satellites is essential. In this lesson, you will be able to derive an expression for the velocity of a satellite, learn the parts of a satellite when launched with different velocities, learn about geostationary satellite and understand the conditions for a satellite to be geostationary, learn the definition of escape speed and derive an expression for it, and understand the concept of escape speed. How should a satellite be launched so that it goes around the Earth in a circular path? To launch a satellite, it must be taken to the required height above the Earth's surface. The satellite is then launched with a particular velocity so that it orbits the Earth in a circular path. For a satellite to be in circular orbit around the Earth, it should be launched with a velocity in the horizontal direction relative to the Earth. Let a satellite of mass m be launched horizontally relative to the Earth's surface with a velocity v. The centripetal force required for a stable circular path of the satellite is provided by the gravitational force of attraction between the Earth and the satellite. Centripetal force equals gravitational force, which implies mv square over r equals gmem over r square, which implies v equals square root of gme over r, where me is the mass of the Earth, m is the mass of the satellite, and r is the radius of the satellite's orbit. Click on Case 1 to observe the path of the satellite if the launch velocity is slightly lesser than square root of gme over r. If v is less than square root of gme over r, the satellite will orbit in an elliptical path with Earth as the far focus. Weather satellites are purposely launched into an elliptical path. Click on Case 2 to observe the path of the satellite if the launch velocity is greater than square root of gme over r. If v is greater than square root of g me over r, the satellite will orbit in an elliptical path with Earth as the near focus. What is a geostationary satellite? Click Answer to find out. As the Earth rotates, geostationary satellite moves in its orbit following the rotation of the Earth. Actually, the satellite seems to be stationary with respect to a fixed point on the surface of the Earth. This is the reason why the satellite is called geostationary satellite or synchronous satellite. Click Conditions to know the conditions for a satellite to be geostationary. Condition 1. The satellite orbit should be concentric and coplanar with the Earth's equator. Condition 2. Direction of rotation of the satellite around the Earth should be the same as the direction of rotation of the Earth. Condition 3. Period of the geostationary satellite should be the same as the period of the Earth's rotation about its axis. Click Height to know the height of a geostationary satellite. Height of the satellite from the surface of the Earth is 3.6 times 10 to the power 7 meters. For a satellite to orbit in a stable circular path around the Earth, the centripetal force is provided by the gravitational attraction of the Earth. Centripetal force F equals mr omega square. Since omega equals 2 pi over t, F equals 4 pi square times mr over t square. Earth's gravitational force on the satellite F equals g MEM over r square, which implies 4 pi square times mr over t square equals g MEM over r square, which implies r equals g ME t square over 4 pi square the whole power 1 over 3. For a geostationary satellite, t equals 24 hours, which equals 86,400 seconds. G equals 9.81 meter per second square. Using the expression for small r, the calculated value of small r equals 4.24 times 10 to the power 7 meters. R plus h equals 4.24 times 10 to the power 7 meters. Therefore, height of satellite from surface of the Earth h equals 4.24 times 10 to the power 7 minus 6.40 times 10 to the power 6 meters, which equals 3.60 times 10 to the power 7 meters. Summary: the speed of a satellite in circular orbit at a distance r from the center of the Earth is v equals square root of g me over r. If the velocity is less than v, the satellite traces an elliptical path with the Earth as the far focus of the ellipse. If the velocity is greater than v, the satellite traces an elliptical path with the Earth as the near focus of the ellipse. A satellite which remains stationary with respect to a point on the Earth is called a geostationary satellite. The geostationary satellite is stationed at a height of about 36,000 kilometers above the equator. The conditions for a satellite to be geostationary are: the satellite orbit should be concentric and coplanar with the Earth's equator. The direction of rotation of the satellite around the Earth should be the same as the direction of rotation of the Earth. The period of the geostationary satellite should be the same as the period of the Earth's rotation about its axis. A satellite in circular orbit around the Earth possesses both gravitational potential energy and kinetic energy. Click GPE to know the expression for gravitational potential energy of a satellite. Gravitational potential energy U equals negative G MEM over R, where ME is the mass of the Earth, M is the mass of the satellite, R is the distance between the Earth and the satellite, and G is the universal gravitational constant. The expression for kinetic energy of the satellite can be determined using the concept that the centripetal force required by a satellite is provided by the gravitational attraction of the Earth. Click KE. Centripetal force mv square over r equals gmem over r square, which is the gravitational force, which implies mv square equals g mem over r. Kinetic energy K equals half mv square, which equals half g mem over r. Click on GPE and KE to know the total energy. Total energy equals gravitational potential energy plus kinetic energy, which equals negative G MEM over R plus half G MEM over R, which equals negative G MEM over 2R. Observe a satellite revolving around the Earth at a distance r from the center of the Earth. The kinetic energy K, gravitational potential energy U, and total energy E of a satellite depend on its radius of orbit as shown. E equals U plus K, which equals negative G MEM over 2R. To know what happens to the satellite when launched with different speeds, first select the speed 5 times 10 to the power 3 meter per second. The missile crashes to the Earth. Select 7 times 10 to the power 3 meter per second from the drop-down menu and observe again the trajectory of the missile. Is the launching velocity sufficient? No. The missile again crashes to the Earth. Select 9 times 10 to the power 3 meter per second from the drop-down menu and observe the trajectory of the missile. The missile moves in an elliptical orbit. A missile fired upwards eventually falls back to the ground due to the Earth's gravitational attraction. Can a missile be projected to escape completely the gravitational pull of the Earth? Click Answer. Yes, provided the missile is projected with a certain minimum speed known as the escape speed. The escape speed of the Earth is the minimum speed of an object to escape completely the Earth's gravitational pull and move to infinity. Select 11 times 10 to the power 3 meter per second 13 times 10 to the power 3 meter per second and 15 times 10 to the power 3 meter per second from the drop-down menu and observe the trajectories. Missile escapes completely from the Earth's gravitational pull. Missile escapes completely from the Earth's gravitational pull. Missile escapes completely from the Earth's gravitational pull. The escape speed can be derived using the principle of conservation of energy. By the principle of conservation of energy, total energy of a body on the Earth's surface equals its gravitational potential energy at infinity. At infinity, R equals infinity. Gravitational potential energy equals negative G MEM over R equals 0. Hence, half mv square plus negative G MEM over R equals 0, which implies V equals square root of 2 times G ME over R, where V is the escape speed. Substituting G equals 6.67 times 10 to the power negative 11 Newton meter square per kilogram square, ME equals 6.02 times 10 to the power 24 kilograms, and radius of the Earth R equals 6.4 times 10 to the power 6 meters. We get V equals square root of 2 times 6.67 times 10 to the power negative 11 times 6.02 times 10 to the power 24 over 6.4 times 10 to the power 6, which equals 11.2 times 10 to the power 3 meter per second. Summary: the total energy E of a satellite orbiting the Earth is given by E equals negative G MEM over 2R. Escape speed of the Earth is defined as the minimum speed with which an object should be projected so that it escapes completely the gravitational pull of the Earth. Escape speed from the Earth's surface, V, equals square root of G ME over R.